A Born Haber diagram walks you through two separate ways to turn two elements into a salt, and then uses those two things to calculate an energy of some particular thing along these two processes. So what I'm going to show you here today is we're going to look at two different ways you can turn lithium metal and chlorine gas into lithium chloride salt. One of them is you can just react them. When you react to them, what you're doing is you're setting up a calculation where the energy change from this starting point to this finish point is equal to two things. It's equal to either your enthalpy of reaction, and in this specific case, you're starting with two elements that are in their standard states, and so this is also equal to the enthalpy of formation of this particular chemical. Okay? However, alternatively, there's a series of physical processes that we can do where we can figure out, starting at this point, a different pathway to end up with the salt. And so if we walk through here and we say, well, how can we take solid lithium metal and chlorine gas and turn it into lithium chloride step by step by step? Here's what you have to do. You first have to change lithium metal as a solid to lithium as a gas. You have to sublimate the lithium, okay? And our chlorine would still stay the same. You have to take the chlorine and break apart the bond. So you have to turn chlorine molecules into chlorine atoms. So the difference here is that we have half a mole of Cl2s, and here we have 1 mole of Cl, so we've broken apart the bonds there. You have to ionize an electron from the lithium to form a plasma, and then you have to add the electron to the chlorine form a lithium chloride plasma. And then the final thing is that these pieces have to come together and form a crystal. So how much energy does each one of these steps take? So from here to here, let's call this step 1. We're looking at the energy required to sublimate lithium. And that is usually going to be provided to you. So some kind of enthalpy of sublimation. And in this case, for this particular one, I found the value to be 159.4 kilojoules per mole. Okay. That value is not in the IB data booklet, and that's going to be something provided to you in the problem, or alternatively, that can be the thing that they ask you to find. After that, we are going to break apart a half of a mole of chlorine bonds. So we're looking at a bond enthalpy, and that can be found in table 11. In the IB data booklet. So when we look up chlorine bonded to chlorine, it's plus 242 kilojoules per mole. But remember that we have Cl2s turning into Cl, so we only need half a mole of Cl2s. So really, we only have to break half this amount. So our actual amount that we're going to provide in energy is going to be 121 kilojoules per mole of chlorine atoms. Okay, so we'll call that step 2. And then in step 3, we have to ionize our lithium. So we're going to look up the ionization energy. And it's the first ionization energy of lithium, which is in table 8 in the data booklet. And that came out to be 520 kilojoules per mole. Okay. Now, all three of those things are endothermic processes, so we're increasing in energy between the first, second, and third step. The fourth thing we need to tabulate is how much energy it takes to add an electron to chlorine, and that's actually an exothermic process, but that is our electron affinity, which is also in table 8, like the ionization energy. So when I looked up this particular value, it was a negative 349 kilojoules per mole. Okay. And we have one more thing we have to do. We have to take these, which are now in the gaseous state. So we have a lithium ion here, and a chloride ion here, and a chloride here, and a lithium here. And we have to bring all of them together to form a salt crystal. And so we're looking at kind of the reverse of the lattice enthalpy or the lattice energy. So our fifth step here is our lattice energy. And that is in the data booklet in table 18. And the value we find for that is 864. Now, lattice energy is defined as the energy required to separate the ions from one another. So in this case, we're bringing them together. So there's kind of two ways we can attack this. My personal preference for these problems is I like to set up the entire left side and have it be equal to the entire right side, because I know from here to here is the same difference in energy. But alternatively, we can do this with a consistency of signs. So these are all endothermic processes. This is exothermic. We know that this is exothermic in the way that we're traveling here. So one of the things we can do is we can set this enthalpy of formation equal to step 1 is 2 plus 2 plus 3 plus 4 plus 5. Now if we do that, we need to use positive signs for 1, 2, and 3, and negative signs for 4 and 5. And they should add up to this. So our enthalpy of formation is going to be equal to step 1 plus 2 plus 3. Let's try that again. So our enthalpy of formation here is going to be equal to step 1 plus step 2 plus step 3. And then we're going to be adding to that step 4, which is going to have a negative sign. And we're going to be adding to that step 5, which is also going to have a negative sign. So we're going to do 1 plus 2 plus 3 plus 4 plus 5, but these two will have negative signs and we'll get our enthalpy of formation. For me personally, I like to just get rid of all of the signs. I like to do the enthalpy of formation, or the enthalpy of reaction, if it's not. And then I like to add to that the enthalpy of sublimation. And I like to add to that the bond enthalpy. And I add to that the ionization energy. So I do this plus this plus this plus this, those four things is equal to the lattice enthalpy plus the electron affinity. So this plus this. So personally I do that, and then I just ignore all negative signs. I do everything as a positive. And then at the end, I go back through, and if I need to figure out what the enthalpy of formation is, then I go through and say, okay, well, should this be a positive or negative based on the particular settings? That will, generally speaking, work, but you could run the risk where if that were somehow an endothermic process, you might not figure that out. So the for sure way to do that would be this way, but this will usually generally get you the right answer without too much trouble.